Welcome to Dr. Gong-Yu Liu's Nanotechnology and Surface Chemistry Lab. My name is Terell Keel, and I'm a third-year graduate student in the Liu Lab, and I'll be your guide and narrator in this virtual lab tour. Our focus is the application and development of nanotechnology. This deals with the design, engineering of nanostructures, bioreceptors, biosensors, and reaction sites precisely positioned on a surface. So this means single cells, proteins, molecules, and atoms. Before we jump into the lab tour, it's good to go over a few basics. What is nano? Nano is a scale meaning 1 billionth. So a nanometer is 1 billionth of a meter, or 10 to the negative 9 power. So nanotechnology deals with a scale range between 1 to 100 nanometers. Let's put that into perspective. A typical ant is about 1 millimeter in length, which is 10 to the negative 3 meters. Red blood cells are about 7 to 8 microns, and microns is 10 to the negative 6 meters. Viruses are about 100 nanometers in diameter, and we know that's 10 to the negative 9 of a meter. Small molecules, they range from 1 nanometer to just several angstroms, and an angstrom is 10 to the negative 10 of a meter. Why is nano so important? As technology and science progresses, we're learning that the future is small. Smaller electronics, smaller transistors, capacitors, nanomachines, and biosensors. But how do we see into this world? Can't we just use regular light microscopes? Unfortunately, we can't use regular light microscopes. Light microscopes are limited by the wavelength of light used to probe the sample. So at best, optical resolution is about 200 nanometers, which will get you in the ballpark of nano, but it's orders of magnitude away from seeing actual atoms. But don't despair. Scientists have developed instruments to surpass these limits. I will briefly go over a few instruments that we use in our lab. SEM, scanning electron microscopes, use a probing source smaller than light, electrons themselves. They can scan the surface with a focused beam of electrons, and they can achieve resolution better than 1 nanometer. STM, scanning tunneling microscopes, can image surfaces at the atomic level and can distinguish features smaller than 0.1 nanometers. A current is applied under a bias between the probe tip and the sample, and electrons jump from the tip to the sample. This can be used to make topographical maps of the sample's surface. Similar to STM, AFMs, atomic force microscopes, use a sharp probe to map out the topography of a sample surface. It works a lot like a record player, with the tip feeling the van der Waals attractive and repulsive forces on the sample. A laser is used to record these small changes in topography, and features as small as 0.5 nanometers have been resolved. Confocal. Well, it's an optical imaging technique used to increase the optical resolution and contrast of light microscopes. It uses a spatially positioned pinhole to block out of focus light in the image formation. With confocal microscopes, you can compile slices of your sample. Our lab focuses on scanning probe technologies, and we house several AFMs and AFM type instruments. We have 2 SEMs, an SEM, and a few other instruments that help us with our surface chemistry projects. Drug delivery into cells, precise positioning of atoms, molecules, proteins onto cells and surfaces of all kinds are all made possible with our specialized instruments. And with the help of a few of my lab mates, I will show you some of the cool instruments that we have in our lab. Okay, let's get to the instruments.
Hi everyone, my name is Wong. I'm a second year graduate student in Dr. Liu's group. Here's here's my favorite baby. This is our fluid FM. The stages for the samples. We have the stages for the probe. We have the AFM head inside the instrument. You won't be able to see it, but it's there. It works like an AFM with a scanning probe. The only difference is we have the tiny little openings in the apex of the scanning probes. So with that hollow fluid FM probes with apertures down to 300 nanometers, there are so many applications. There are bio applications. You can use it for 3D nano printing, you name it. Alright, so here's our working station for our cyto search instrument or the fluid FM. This is our computer. Here's a nice scanner. The probes come with the QR code that we can scan with. The computer we use to analyze the data and look at the samples. This is another instrument we use for nano printing, nano 3D printing. And over here, we have the cool stuff. We have this hand-built CAN AFM, which offers super high resolution, and it also looks cool.
Hello, my name is Cody Chalker. I'm a postdoctoral researcher in Liu's Lab in the Department of Chemistry at University of California, Davis. I'm also the technical director at the Keck Imaging Facility. And today I want to talk to you a little bit about Raman Spectroscopy. As you can see here, this is a Raman Microscope. It uses a monochromatic 785 nanometer laser, and it goes through an assortment of filters that ultimately goes down to a sample and goes to a detector. And what it's measuring is the phonon or vibrational modes of solid state materials. Basically a fingerprint, vibrational fingerprint for identifying different types of materials such as pharmaceuticals, novel 2D materials, biological materials, basically almost anything you can think of. Hi, it's Cody. Today I want to talk to you guys about scanning electron microscopy. This is a Hitachi S4100 scanning electron microscope. It's a little bit older, it's from 1986, but it's one of the first field emission scanning electron microscopes that has resolution down to about 2 nanometers, which is pretty incredible. So right now we have a sample in here. We actually have an ant, and I have done everything in terms of adjusting the focus and stigmation. So instead of using light to look at these specimens, we're actually using electrons. So we have an electron gun coming down a column, and it's being focused with electromagnetic lenses. It hits this sample right here, and it's detected right here by a secondary electron detector. So you can see right here, we can see the head of the ant, and if we want, we can go in looking at the eyeball. So you can see here, I'm zooming in. Let's take a little image of it. You can see this is the ant head. We're going to zoom in right there. Scanning tunneling microscopy is a technique to overcome the diffraction limit of traditional light microscopes. And what it does is we take a sharp probe, like a electrochemically etched tungsten tip or gold or platinum. We can even cut it ourselves with pliers. And you bring it in close proximity to a surface. You measure the current between the tip and the surface when a voltage is applied, and you have a feedback control system that adjusts the piezo to move up and down when it's raster scanned over the surface. And so you can see that the sensitivity is really high, so we get atomic resolution because the current that we're sensing is exponentially dependent on distance. So here is one type of scanning tunneling microscope that can be operated in air or in liquid. And so you can see here, we have all these wires here that go to tubes that will walk down a ramp. And in the middle, there's a tip that can then approach the surface. Okay? And then again, we have this transit impedance amplifier here to measure the current signal. So although this is really nice, we need to have a nice vibration isolation and acoustic isolation because these are really, really sensitive measurements. This can also be done in ultra-high vacuum. Ultra-high vacuum scanning tunneling microscope with the same design, but now it's under, again, we call it UHV, ultra-high vacuum. And you can see here, in order to manipulate things, we need something called a Wobble Stick. And you can see it's on a vibration isolation unit. And I can move things in and out of this vacuum system
And because it's in vacuum, it's much cleaner than it would be in air because of absorbates and moisture.
One course microscope, it's called the Confocal Microscope. Right now, I am actually imaging a piece of gold. And what you can see here, this is the inverted microscope for the confocal. And this part right here is the AFM head, atomic force microscope head. And my sample is laying down. I have piezo scanners that are moving forward, backward, up and down to do this raster scan. And then my head right here has a Z piezo that will move up and down based off this feedback loop. And you can see here in this image, you can see actually right now I'm imaging. There's a laser that hits the back of a cantilever that we've micro-machined using wet chemical etching methods. And this laser hits the back of the cantilever and then hits a photodetector. This is allowing us to be able to see our steps here. So this is gold 111 single crystal. And so we should expect to be able to see atomic steps. For the confocal, we have an assortment of lasers, about 9 to be exact, and they would go through these fiber optic cables, through the inverted microscope, through an objective, strike the sample depending on what your emission wavelength is, and would hit a photomultiplier tube that is back here. And you would see images such as this with a confocal microscope, detailing, say, nucleic acids, proteins, or the actin filaments.
This concludes our virtual tour. Thank you for taking the time to check out our lab. Making this video was challenging and fun. And if you're interested in our lab, check out our website at the bottom. Peace.